Hi and welcome to Connected Particles Lesson 4. We're going to now look at two problems where we've got a car pulling a caravan or a trailer, or two objects connected by some string over a smooth pulley. So we're going to look at cars and caravans in this lesson, and then the next recording we'll do objects connected with a string over a pulley. Okay. There are a couple of modeling assumptions that we need to know when we're looking at cars and caravans. The first is that we assume that these objects are connected by some light, inextensible string. Now, these words light and inextensible have a very mathematical meaning. So inextensible means that it doesn't stretch. That's relatively obvious, but what that means is, therefore, if I've got two objects connected by a string, and if I start pulling this one, let's say I pull it with some acceleration 2 meters per second squared, then this one must also travel with exactly the same speed and acceleration. Okay, because they're connected by this inextensible string, it's not possible to take this object and extend and stretch it or pull it without the other one. That would be like having a spring or a string that would stretch. That in this case, that's not possible. So it just means these numbers here apply to both objects at the same time, and they don't change. The word light means that the mass of the connection, the string, can be just completely ignored. We don't have to worry about adding some weight to the weights of the objects. We just consider the weights of the objects. And then finally, the tension is the same throughout the string. So if I have an object here, let's scroll down a little bit. If I have an object here and it's on a string, what we're saying is that tension in that part of the rope there will be equal and opposite to that tension there. Essentially, Newton's third law. If it were a chain, like a heavy metal link chain, then you could argue that the weight of this, let's say this is, I don't know, 1 kilogram, this chain link here would have to have a tension to hold 1 kilogram, so 1 times G. But then the tension in the next link would be would have to hold the weight of that link and the box. So it will be 1G plus whatever the weight of the next link is, say 0.1 times G. And then the one in the next one would be the weight of the box plus the weight of the 2 links below it, and so on and so forth. So you get different tensions going up the chain. The same would be true if you just had a heavy rope, but we're just going to assume that that's not the case. And so in terms of cars and trailers, we can just assume that the tension in that part that this object is pulling this object back with will be equal but opposite to the tension that this object is feeling being pulled forward by this object. Imagine it's a car going in that direction. Okay, the trailer is trying to slow down the car because it's connected to the car, and the car will feel the pull of it being pulling it backwards as air resistance holds it back. And then the trailer will feel the pull of the car trying to pull it forwards. But those two forces are equal and opposite according to Newton's third law. So let's try and apply these modeling assumptions to all the rest that we know. And we're going to be using Newton's second law, F equals ma, as no surprise. But again, just to remind you, we want to be following the steps that I highlighted earlier here. Read the information carefully. We might need to read it a few times. Draw a general diagram to understand what's going on. Draw a second set of diagrams, one for each object, to help you understand all the forces that they experience, and then apply F equals ma to both, giving us simultaneous equations that we can then solve. So let's do that. So here we have a car pulling a caravan. And so we're going to try and draw the whole situation. It's, there we go, funky shaped caravan, being pulled by some big car. This is nice and light, so we'll label this as 400 kilograms, and this is now 1.2 tons. Everything has to be in standard units, so we've got to write it in kilograms. We've got a driving force of 600 newtons, so let's label that there. Sorry, 6,000 newtons. What other forces? Assuming there are no resistance forces, okay, so that makes it easier. And we're being asked to find the acceleration of the caravan and the tension in the string. So let's label that. The tension will be there and there, okay, equal and opposite forces, because these two things are in contact. So now what we're going to do is just draw these two things separately. Now you may not need to, but I'm going to follow my own advice. You might decide that this is simple enough that you don't need to. Okay, the caravan only experiences one force, and the car is experiencing two forces that we care about. Now, it's not quite true that it's only experiencing one force. There is also the weight of the caravan and the normal reaction with the floor with the caravan, and the same again with the car, the weight of the car, and that begins with C as well. Oh, well, okay. And the normal reaction. So we have to be a little bit careful there, but we're not interested in those green forces. We're only interested in the horizontal forces because we're only interested in the fact that this thing is going to be accelerating in this direction. So we want to know what that is. So I'm going to take that as my positive direction. Let's apply F equals ma to both of these. So we're going to do this horizontally. And again, F equals ma for this one too, also horizontally. So the first one, we just get a very simple T equals 400 times A. And here we're going to get 6,000 minus T, because T is opposite to our positive direction, equals 1,200 A. And we can solve this simultaneously. We can substitute one into the other. You could type it into your calculator to do it for you. It doesn't matter. Let's substitute this into here. So I'm going to call that 1, call that 2, and so 2 little notes like this make it a lot easier when the examiner is reading your work. I highly recommend it. Minus 400A equals 1,200A. So we're going to get 6,000 equals 1,600A. And we're going to get A equals 1.75 meters per second squared. Notice there is no need to round this. We're not using gravity, and we're assuming that all the other values in this mathematical question are exact. That's not true in physics. You'd have to round this to one significant figure because we've only got one significant figure in our question. But when it comes to the maths A level, it's only the value for gravity that determines what accuracy we have to give in our answer. And since we're not using it, we can quote as much accuracy as we like. And finally, we're just going to sub that into up here. Sub into 1 to give us that T equals 400 times 3.75, and so we're going to get 1,500 newtons, and that's the tension in the string. Just reread the question, we've answered that, we have our solution. What modelling assumptions have we made? Firstly, we've assumed both of the two things already, that the car and caravan, sorry for the bad writing, are connected with a light, inextensible string. This means, we've got to state this as well, we can assume therefore that they are accelerating with the same acceleration. And it's part of our assumption. Therefore, both accelerate at the same rate. Okay. The other assumption is actually stated in the question. Assuming that there are no resistance forces, it might be worth stating that. With the word questions, it's worth just stating everything you possibly can. Right there. There is another way to answer part of this question. We have taken this whole diagram and we've split it into two separate pieces. This method will solve any question. But there are some questions like this one that we can use a slightly different method. So let me show you how you would do that. It's slightly different. So here's my caravan, here's the car. You can tell I should never have become a graphic designer. And instead of treating it as two separate objects, I'm going to treat it as one big object with a force of 6,000 newtons. Okay, there's no resistance forces. The internal forces and the tension cancel each other out, so we don't need to consider that at all. And so we're left when we apply, oh yeah, and the mass of this thing will be the combined mass of both objects, so 1,600 kilograms, the summation of the two before. And so now we can just apply F equals ma to the whole object, and we're going to get a single driving force is equal to the total mass times acceleration, and then we can divide them again, we're going to get A equals 3.75. Notice though that it doesn't tell you anything about the tension because the tensions cancel each other out. We can only use this method to answer that part of the question. We would then need to do this method to find the tension in the cable that pulls them or connects them. So I think it's often worth just going through this method straight away. Have a go at this question here. See what you can do. There's a video. My solution is coming up now. Here we go. So here we'll, oh dear, that wasn't meant to happen. There we go. Sorry about that. Here we have a little boat on some trailer. There we go. Connected to my car. There we go, a little bit more artistic detail this time. And we're going to try and put this information on here. So we're going to get 2,000 newtons. We're going to have tension in the cable here. But notice they've also got resistances. So this time we've got the 2,000 newtons, we've already done that. And we've got the car experiences 700 newtons. We're starting just to get a bit complicated. I mean, they've got 700 newtons going on here. We've got another resistance force of 800 newtons. Whether they left the sails up while we're driving along, that was a mistake. We've then got this one is 700 kilograms, this is 900 kilograms. And so trying to do calculations from a diagram like that can get a bit confusing. which is one of the reasons why I highly recommend redrawing it. Just keep it simple. So here's my boat, and we'll just label all the forces on it. So we're going to have the tension from the car. We're going to have 800 newtons dragging it back, 700 kilograms weight. And we could include the two forces that we don't need. Its weight and the reaction force pushing it up, but we're only going to be doing horizontal forces. Then let's just take this part for the car. So here's the car, and we're going to 2,000 newton driving force, same but opposite direction tension, 900 kilograms, and again, two forces that we don't need. We don't need to worry about the weight or the reaction force, the normal reaction force. Okay, so let's apply F equals ma horizontally to the boat, and we're going to get, now, it's accelerating in this direction. They're both accelerating together, so I'm going to take that as my positive direction. So we'll have T minus 800 equals 700A, and over here for the car, again horizontally, we're going to get 2,000 newtons minus the tension, because this time the tension is negative, going in the opposite direction to our direction, equals 900 times A. Now we have, again, two simultaneous equations. If we rewrite them like this, T minus 700A equals 800, and 2,000, sorry, made a mistake, let's come back to this. Forgotten the 700 Newton resistance force, forgive me. So let's rewrite this. This would be 2,000 minus T minus 700. So we're going to get down here, when we simplify this, that minus that is 1,300. And then if we add T to both sides, we get T plus 900A. Okay. So plug that into your calculator to solve that, because it's in the right form for your calculator. And we're just going to get T equals 1,018.75 newtons, and acceleration equals 0.3125 meters per second squared. We could round that to an appropriate degree of accuracy, but there's no need because the question doesn't include gravity, but we will, just in case, so we'll say it to three significant figures. We've got 1,010 newtons, and here, and A equals 9.313 to three significant figures. Meters per second. The last part of the question, it says, explain how the assumption that the tow bar was light and inextensible was used. So firstly, there was no mass to consider, but more importantly, both car and the trailer accelerated with the same acceleration. And that's really important, because that's what allowed us to solve this simultaneous equation. Without that, you couldn't solve this yet. You'd have to do a whole lot of stuff with Hooke's law and all of the joys therein. I hope that is helpful. And there's that solution. Sorry for my scruffy handwriting. Have a go at exercise 19D. Minimum I think you should be able to do is question 2 through 7, but do have a go at the others as well. Have fun.